Hello. Hey, how's it going?
Hey, good. How you doing?
Good, good, good.
Okay, looks like you're up. Yeah, feel free to get started.
Sure. I was wondering before I get started, I was wondering if it'd be cool with you if I record this session and then maybe that's cool with you?
Yeah, no
Oh,
problem.
nice, man. Appreciate it. Okay. So let's see. Um, Island count. Given a 2D array, binary matrix of zeros and ones, implement a function that returns the number of islands of ones within the matrix. An island is defined as a group of adjacent values that are all ones. Adjacent values, okay? And then a cell in binary matrix is considered adjacent to another cell if they are next to each other on the same row or column. Okay? Same row or column. So these ones are adjacent. Note that two values of one are not part of the same island if they're only sharing a mutual corner. So these two cells are not part of the same island then. Explain and code the most efficient solution possible. Okay, and and these will be integers then.
Yeah,
So
all ones and zeros.
yeah, yeah. So based off this example, we can see based off this example we get an output of 6. So so this is one island. This is one island. These three are an island. This is an island. That's an island, and then that's an island. So that's 6. Okay. So so it looks like we'll have to do some sort of traversal through this this matrix, and we can we can look for cells that are cells that have a value of 1, and if a cell that is adjacent to that cell is also a 1, then it'd be part of the same island. So, and then if it's not part of the same cell, then that island stands on its own. And we can do that traversal. We can do something like a depth first search, and we can continue traversing through the cells looking for ones, and then if we reach an edge of the grid or we reach a 0, we can stop that traversal. The okay, so based off of the constraints of the problem, being that the length of the binary matrix will be up to or equal to 100, we could also do a recursive approach to the depth first search. And we could continue that traversal as well, only if we haven't visited the cell before. Because if we visited the cell already, then we already know either it's part of the island. We already know that it's either part of the island or it's not part. So I would have to create a way to acknowledge that we visited the cell, which we can do either using a set or an array containing every position that states whether the cell's been visited, using something like a true or false condition. But a set would be a little bit cleaner. Okay, and then to do the traversal, we can traverse to the left, to the right, up, and below, but not diagonally. So within the recursive depth first search, we can add the directions to the recursive call, and assuming that we haven't visited that cell, or it's not, or if it's within the bounds of the matrix, then that call would be made. So let me see if there's any particular things about this problem I need to note. Okay, okay, that all looks fine. So we can store the length of the rows and the columns in these two variables. And then we can create a set containing the cells that we've already visited. And then for the recursive depth first search, we'll need some nested function called DFS traversal. And that function will take in a current cell that we're visiting. So we can say row and column, and then we'll need to add constraints to that, so that we know we can continue that traversal. So the constraints would be we can say if the binary matrix, if it equals a 1, we can continue. I'll say if not. If it doesn't equal a 1, then we'll stop. Or if the row and the column are in the set already, then we've already visited, so we don't want to keep traversing, and we can represent that using a tuple. So we can say or row column in visited cells. And then we can say the row and the column have to be within the bounds of the binary matrix. So we can say or row not in range rows or column not in range calls. Then for those constraints, if any one of those is true, then we would return. And then if it is, if all those constraints are not met, we can continue the traversal, and at that point we'll have to visit the cells that are adjacent. And to do that, we'll need to first add the cell to the set as a tuple, and then we could add I can create an array of directions that I could then add each direction to the current row and column. So something like 0, 1, 1, 0, -1, 0, and 0, -1. And then I can say for RC in directions, and then I could begin that traversal. And I would need to add the current row value plus the current direction. And then that would continue, or that would do the recursive traversal, and then add every one of those cells that is a 1 and adjacent to the set. And then finally I would have to traverse through the matrix using I could use a nested for loop to iterate through the binary matrix, and then if it's a 1, then I could begin the traversal. So I could say something like island count equals 0. We'll have to return the island count. Just trying to lower the screen, but okay. I could say for R in range rows, for C in range columns, and then I could say if binary matrix row column equals 1, and the row column is not in visited cells, then I could begin the traversal. And then I could increment the island count, because that would mean that we've now begun traversing through an island. Let's see, so if it's not in visited DFS, okay, so that looks good. So row not in range rows, column not in range columns. Okay, that looks good to me. Does this approach make sense?
It does. Excuse me. It does. Yeah, any thoughts? Well, let's first see if it runs successfully, and then we can chat about complexity.
Okay. List out of range. List index out of range.
I think, well, let me know if you have an idea.
Okay. If row not in range rows.
I think it just has something to do with the order of your if conditions on line 10.
I see. Yeah. So it's yeah, if these aren't met, then we can't check this array right here.
Mm-hmm.
Okay. Okay. The time complexity for this, I believe it's O of, you could say M times N, where like M is the length of the rows and N is the length of the columns. And I believe the space complexity is the same.
Yeah, I think so too. You have this set that's your space complexity, and in theory, if you don't have any islands, you can go and just, well, let's think. Yeah, like, or if the whole thing was an island, you would keep going through and adding every cell to the set. So in worst case, could be O of n times n for space complexity.
Okay.
Any other approaches? I mean, well done. You got all the tests to pass. Any other possible ways you could approach the problem?
Yeah, I could approach this using a breadth first search. And one thing that is important to always note is that the the amount of recursive calls that are allowed. If in the case that the length of the binary matrix was very large, then I wouldn't take the recursive approach to this. I would probably use a breadth first search, in which I would go to a cell and then add that cell to a queue and then check its adjacent cells and then keep appending those cells if they're valid to that queue.
Yeah, say more about why, if you had a very high in and m value, what about, say more about why you would choose BFS over DFS there.
Yeah, because there's only so many amounts of recursive calls that you can make before the call stack won't allow anymore. So you'd in that case, in the case that it's like the length of the binary matrix is like 1,000,000, then you'd want to take the iterative approach, because I think Python allows 1,000. Usually, I think it's 1,000 recursive calls before the call stack is full.
Nice. Yeah, well done. Any other thoughts or comments before we move on?
Nope. I'm ready whenever you are.
Cool. Nice job. All right, I'm ready to swap.
Okay.
All right, merging two packages. Given a package with a weight limit and an array of item weights, implement a function, get indices for item weights, defines two items whose sum of weights equals the weight limit. Your function should return a pair ij of the indices of the item weights, ordered such that I is greater than j. If such a pair doesn't exist, return an empty array. Okay, time and space complexity. So this is like a two-sum problem. And my thoughts are we could do like a two-pointers approach, or we could do a hash map. But let's walk through this example to make sure I'm thinking about this right. So this is saying it's a limit, implement a function whose sum of weights equals the weight limit. Okay. So, and I'm returning the indices in descending order. And are they distinct? Interesting. Let's see. Doesn't say explicitly that the weights are distinct, so I can think about that. Okay. So for this example, we have so the naive solution would be like nested loops. You have like I and j pointers, and you start at like I, and then j is I plus 1, and then you loop through, and then let's see, is there only one solution? Let's see. Finds two items, should return a pair if such a pair doesn't exist. So it seems like if there are two possible solutions, I could just return the first valid one. That seems right, but
yeah, I think either one would work.
Okay. So in this example, I'm adding 4 plus 6 doesn't equal 21. 4 plus 10, no. 4 plus 15, no. 4 plus 16, no. Then I have 6 plus 10, no. 6 plus 15, yes. And in that case, I have my indices, and I would just return the greater of the two. So the brute force solution should be O of n squared. Then I could get an O of n solution by looping over the array, storing all of the values in a hash map. And then I would when I do that, I would have to store like the value and as like the key. Sorry, I would have to store both the key and the index so that I could have something to return. But then I would just loop through the array again, and I would say, okay, for each number that I'm iterating over, is there a number in my hash map that is equal to, like, you know, the difference between the number I'm iterating over and my limit? If that does exist, then I would return, I would just return that pair. And I would know that the value in the index value in the hash map would always be first in my response array, because it would be a higher index than what I'm iterating through. The only funky thing would be if I have duplicate values. Is this sorted? Sorry, I should have thought about that for a second.
I should note that the problem doesn't explicitly say that it's sorted.
Okay. All right. If it was sorted, I would be more confident doing a 2-pointers approach, having, like, you know, if this is my input array, I would have a pointer here and a pointer here, and then walk backwards. But if it's not sorted, then that would be a little more complicated. So I'm just gonna do, I think, what I was thinking originally. So yeah, let's do that. So is map a keyword? I think it is. So, like, let's call this weights. And then length of the array. I could say, like, if this doesn't include this value, I mean, I'm gonna treat this like there are distinct numbers in the list at first, and then if one of the test cases tells me otherwise, I'll think differently. But I think what I can do is just do this, like, weights of, let's do the actual value as the key, and then, like, the actual number in the array as the key, and the value as the index. So at the end of this, I should just get, like, you know, it'll be like, oops, you know, and this will be like 0, 6 will be 1, something like that. And then again, I can just I loop through it again. So we're like for I and just copy this. And then find a difference. It's equal to my limit minus the number over which I'm iterating. And then I'm trying to see if this is in. So the thing is, though, I don't necessarily want to get the same number. So like imagine if here I had like a limit value of 8, I wouldn't want to get 8 and 8. So my thought would be if if weights diff and weights, I think that's valid. I would do something like this. I would return the index of the diff and I. And if I don't find anything, I'd return an empty array. Okay, so I'm taking the number, storing it in weights. Okay, with the index, I'm going through my array again and saying, I want to see if this diff value exists. If it is in my map, I want to return the appropriate indices. I'm going to just run that, see what happens here. Okay, let's just try it with our test case. This is this.
Nice.
Okay. So let's see what happens with the tests. Yeah, I think it's going to be like a duplicate value. So how would I handle the duplicate? So let's just walk through what would happen here. This is going to, I'm going to have like 4, 0, 4, 1, 1, 2 in my map.
Well, not necessarily though.
Yeah. Okay. Yeah, because it'll override. Interesting. So what did I give? 2, 0. This is actually interesting. So for this situation, I would okay, so it's just overriding for iron rangers, it's going through. I'm saying, hey, look for the key of 4 and set it equal on the first pass, equal to 0. On the next one, you're going to set that equal to I, and for the second 4, it should override. And so I would think I would end up with something like that. But that might not be right because I'm returning a 0. So what happens when I then loop over? I'm saying diff, so for the first one, I'm saying, hey, I see. Expected 2, 1, actual 2, 0. And function I is greater than j. That's funny. Based on what the problem is saying, I think, like, it's not obvious to me. I get that I could get it to respond to 1, but it fulfills the case of, in the response, I being greater than j. And those are both valid indices.
Good point. That is a good point. I'm good.
But I'll see if I can make a change to, because I think what it's saying is, okay, well, maybe let's find, like, the maximum indices to provide a valid answer. In that case, I could see like the diff is equal to 4. Sorry, no. For the first iteration, diff would be equal to 1. And so if that is in weights, return. Okay. Diff in weights. I could add another condition here. I feel confident there's a more elegant way of doing this, but I could say something like, if which it will be, but this would be like, I see, this would be, that's the index. I could do this. I think that'll pass this particular case. But let's see. Let's just try running this one explicitly. Yeah, let's see if that works for the others. Okay. All right. So, yeah, now that worked if in the case where I overrode, but now I have both. And so now I'm wondering, I could do something slightly different. Where instead of using a map, I could have a set. So, and then to determine so, I mean, what would be nice is if I had something like this, but obviously this isn't possible because I have the same key values. What I could do is I could, if the number is there, you know, I could store the indices like in a list. And so I would have something like this. This would get a little trickier though. So how would this work? If I were to then loop over and like on line 7, the diff would be equal to 4. If diff is in my map, which it is, I would return okay, so this would be like if this is not very elegant anymore. Okay, so if the diff is in, okay, my map, and then, okay, let's think about this for a second. Maybe instead of doing something like this, I want to say like, if the diff is equal to the number so something like if diff is equal to that,
And if you'd like a hint, let me know.
Yeah, I think with the direction I'm going, I'm just gonna kind of pile in if conditions to solve for the test case, but I'm not thinking about the most general case. So yeah, if you have a hint, that'd be great.
A hint for the solution that they would give, or for the code that you've given.
um, yeah, I've a feeling there's kind of a simpler solution that they have.
Yeah, I think you should think about the idea of a the complement of one number. If that complement exists in the dictionary already,
Mm-hmm.
then you're already good, and you don't need to use more than one loop.
Mm-hmm.
So if you're adding a
Mm-hmm.
value in an index to a dictionary,
Mm-hmm.
then you can just check if its complement, if you've already seen its complement.
Mm-hmm. Mm-hmm. Mm-hmm.
And that would mean that you don't have to
And go
necessarily,
back over and
yeah,
then worry about these like duplicate situations.
yeah,
Yeah. Yeah. Um, it would be here. So like if so this is yeah, the number I'm looking for. If that is in the dictionary already, I can return, and that's going to be in the past. So I would want to return I, and then if it isn't, then I would just add it to the dictionary. And that's fine if there's a duplicate, because for this example, before I add it, I would see that 4 already exists. And as I keep going, if I need a 4 in the future, I want the bigger 4. So I could just override that value. Yeah. And then if I get to the end without finding a solution, so I potentially don't need any of this. Let's see what happens for this test case. Expected to 1, actual 1, 0. Okay, so this is diff equals, so that would be 5 minus 4 equals 1. So that, okay, and that would then set weights of 4 equal to 0. So I would have that. And then on the next one, it would say diff is equal to 1. That's not true. So then do that. And then for the third, it'd be 4. And if that is there, it is. And return I, which is 2, and weights. Sorry, 4 again. Wait a second. So if it's going to go over once, if diff is in weights, it's not. So you're going to set 4 equal to 0. And then go over again. and you're going to be looking for 1. It's not there. So then you're going to override. No, it's not weights of diff. It would be this. Yeah, let's see what happens there. Yeah.
Nice.
Okay. Yeah.
Awesome. And what do you think the time and space complexity is for this?
Oven. Worst case, it's going to get to the end of my list. And worst case, it will add all numbers to my dictionary. I don't think there's a faster way to do this. Again, if it was sorted 2 pointers approach, you could try to get to like a login solution, but with an unsorted array, I think this is as fast as you can get.
Yeah, looks good. Cool.
Well, nice.
All right.
Well done on your problem, and nice to meet you.
Nice to meet you, man. I'm Brandon. So yeah, I recorded this. I don't know if you have a LinkedIn. If you want me to add you to like the LinkedIn, I'll probably make a post of it if that's cool with you. It'd be good for like networking, I think.
Sure.
Okay.
Yeah, sounds good.
Awesome.
Yeah. How about I'm Dave, by the way.
Good to meet you, man.
Yeah, I'll just. What's easier, if I send my LinkedIn to you now, or just through the connection thing at the end?
Yeah, just the connection thing is cool. I'll add you if you click that the thing.
Yeah.
All right.
Awesome.
Appreciate it, man. Take care.
Yeah, you too. See ya.
See ya.